Good morning, students. Till yesterday's class, we solved the problems up to example 5. That is simply supported beam with point load with by the double integration method. In this class, we will discuss about the example 6, that is simply supported beam with UDL by the same method, that is double integration method. And after this, we'll go for Michaelis method, how to solve the problems by using Michaelis method, how to integrate the given curvature equation by the Michaelis method. So let us go for the example 6. It is a simply supported beam of length L subjected to uniformly distributed load small w per unit length over the entire span. Find the maximum slope and deflections in the beam. So look at the problem. Look at the diagram. The beam which is supported at ends A and B, okay, which having the length capital L and UDL value is small w. That is uniformly distributed load acting over the entire length of the beam. So upon application of the load on the beam, which bends like an Markov cycle shown in the figure. So from the diagram itself, we can say that the maximum deflection occurs at the center of the beam, and the deflections are 0 at the supports, isn't it? And the slope where the maximum deflection occurs, the slope is 0. If you draw the tangent to that curve after bending at the center, it is an horizontal position. So that means the slope at the center is 0 and the slope at the supports are maximum. Slope at A is clockwise slope, that is clockwise angle of rotation, and slope at B is anti-clockwise direction. So slopes are equal at A and B by symmetry of the diagram. The slope at this point, slope at A point is this, and slope at point B is this. If we draw the tangent at the A point, the tangent like this, and if we draw the tangent at a point B for that curve, it is a slope at B and this is a slope at A, theta A. But these magnitude wise, these two are equal, but direction wise it's opposite. So this is a clockwise slope, which is positive, which is taken as positive, and the slope at point B is anti-clockwise direction, it is taken as negative. So theta B can be written as minus theta A. If we find the slope at A, after getting the slope at A, simply we can say that it is a negative of slope A. Slope at A is equal to slope at B. And the maximum deflection occurs at the at the center. If we draw the tangent at center for that curve, the tangent is like horizontal position. So angle of this horizontal line is 0. Therefore, slope at center is 0. Let us take the center point is C. If they take the center point is C, theta C is 0. Okay. So let us go for the problem. Consider XX section at a distance of x from the left support. Always you have to consider the x from the left support, XX section. And bending moment XX at XX is, let us take M is the bending moment at XX. Before going to find the bending moment at XX, we have to know the reaction forces at the supports. First of all, in simply supported beam, you have to find the reaction forces at the supports. So from the diagram itself, we can say that RA plus RB, that is upward forces, is equal to downward force. How much downward force it is? So W is the UDL value per unit length. If it multiplied by the length, we can say we can get the total load acting on the beam, W into L. It is the load per unit length into length. If we multiply the length, we can get the total load on the beam. RA plus RB equal to WL. And by taking the moment at A, if we take the moment at A, RB into L and W into L into L by 2. W into L into L by 2 is the moment about A for the UDL value. So RB into L it is in anti-clockwise direction, and the clockwise direction movement is WL is the load which is acting on the beam, which is concentrated at the center of the beam, because it is the rectangular load, or UDL is also called rectangular load. The load which is concentrated in the rectangular load at its center point, that is center of gravity. The center of gravity is at the center of the rectangle. So that is L by 2 distance from the support, left to support. Therefore, WL into L by 2 is the moment of that UDL about support A. So from this, we can say that RB is equal to WL by 2. The LL cancel, one L is cancel, remaining is WL by 2. If RB is L by 2, WL by 2, RA is also WL by 2, because the both supports at the both supports reactions are same. So total load acting on the beam is WL, which is shared by the supports equally, WL by 2, WL by 2. After getting the reaction forces, we can write the moment equation about XX. So how to write the moment equation about XX? Bending moment at XX means the moment developed by all the forces on the right side of the section. So what are the forces on the right side of the section? Here the RB is there on the right side of the section, and also UDL from this place to this place, UDL is also there. So how much distance it is? This distance is L minus X, isn't it? The X is taken from the left support, total length is L, therefore the remaining length is L minus X. So M is bending moment at XX is equal to RB into L minus X. It is in anti-clockwise direction, which is taken as positive. So RB value is WL by 2, WL by 2 into L minus X. Next, the moment developed by the load about XX. Moment developed by the load means W value is there per unit length. Total length is L minus X. So W into L minus X is the load acting on the right side, into which is acting at a distance of half of the distance. This is half of this distance. So L minus X by 2. From this place, L minus X by 2. From the section to load concentration point is L minus X by 2. So that's why I'm multiplied with L minus X by 2. Then we can get the moment of the UDL value about XX, which is negative. Why it is negative? It is acting downward direction, which develop the moment about XX in clockwise direction. So clockwise movement on the right side is taken as negative. Clear, students? Anti-clockwise movement on the right side is positive. Clockwise on the right side movement is negative. So this is the moment equation. From this we can common W by 2 is a common. Here W by 2 is there, and here also W by 2 is there. If we take the W by 2 common, L into L square, L into minus X minus LX minus, it is L minus X whole square. L minus X whole square minus L minus X whole square, A minus B whole square formula, A square plus B square minus 2AB, like that. The minus is there in front of that. So minus L square minus X square plus 2LX. A is the L, B is the X, 2LX. This is the, after elaborating this expression into by simplifying that expression, we can get this formula. M is equal to W by 2 into L square minus LX plus minus L square minus X square plus 2LX. From this, L square minus L square is cancelled. Next, we have 2LX minus LX is the LX plus LX minus X square. So LX minus X square, W by 2 into LX minus X square is the final equation after simplifying that equation. So W by 2 into LX minus X square is the simplified equation. This is the bending moment about XX. So we know that from the curvature equation, we know that the curvature equation is EI d square y by dx square is equal to minus m is the curvature equation, isn't it? So upon substitution of bending moment equation into this curvature equation, EI d square y by dx square is equal to minus m is there. Here W by 2 LX minus X square. Therefore W by 2, if we reverse these parameters, we can cancel the minus value. So W by 2 into X square minus LX. Dear students, from this to this step to this, W by 2 into X square minus LX. As earlier in the problems, in the same procedure, by integrating the curvature equation, we get the slope equation. And if we integrate once again in the curvature equation, we can get the deflection equation. So upon integration of once, ei dy by dx is on the left side, w by 2, x square integration is x cube by 3 minus lx integration lx square by 2 plus integration constant c1. Clear, students? X square integration x cube by 3, x integration x square by 2. So x power n unte x power n plus by x plus 1, x power n plus 1 by n plus 1. Raskochu integration lo. So by integrating once again, if we integrate this equation once again, we will get the deflection equation, that is ei into y. If we integrate dy by dx, we'll get y value on the left hand side. On the right hand side of the expression, w by 2 x cube integration x power 4 by 4. So x power 4 by 4 into 3 is 12 minus L into x cube by 3. 3 into 2 is 6, Lx cube by 6 plus C1x plus C2 is the another integration constant. So this is the final expression including constant values, C1, C2 values. How to get the C1, C2 values? The C1, C2 values will be determined by the boundary conditions of the given beam. So what are the boundary conditions? By looking at the diagram, we can say that the boundary conditions are here at A is deflection 0, at B is also deflection 0, isn't it? The beam doesn't deflect at supports after applying upon application of load on the beam. So we can write the boundary conditions are at x is equal to 0. What is mean by x is equal to 0? If x is equal to 0 means the section will be considered at support A. If x is equal to L, x is equal to L means if the section is considered at support B, isn't it? So therefore x is equal to 0 means support A, x is equal to L means at support B. So what is the x is equal to 0? At x is equal to 0, which parameter is 0? Deflection is 0. So y 0, isn't it? At x is equal to L, also deflection 0. The beam not deflecting anymore at the supports, okay, after application of load. So we can write the boundary conditions for this. We can say that at x is equal to 0, deflection 0, at left support deflection 0, and also at x is equal to L, that is the right support, also the deflection is 0, deflection of the beam is 0, because the supports are there at the left and right hand side. These are the two boundary conditions. We can use these boundary conditions to calculate the constants of integrations C1 and C2, isn't it? So from the boundary condition 1, what we said that from the boundary condition 1, at x is equal to 0, wherever the x 0, we have to substitute the y value 0. If you substitute this boundary condition into the deflection equation, if you substitute y place 0 in place of y 0, then you must substitute the x is equal to 0. Upon substitution of 0 value at x place, these three parameters are 0. Therefore, the remaining value is C2, y0, therefore C2 is equal to 0 from the first boundary condition. Clear, students? Next, from the boundary condition 2, what it is at x is equal to L. If you put the x value is L, then the deflection y is also 0. So from this boundary condition, we can say that y0 means the left hand side 0, that is equal to w by 2 in place of x. What the x value here? L value. So L power 4 by 12 minus L into L cube by 6 plus C1 into L. C2 value is 0. We can neglect the C2 value in this equation. So W by 2, L power by 2, L power 4 by 12 minus L power 4 by 6. So 12 is the LCM. L power 4 minus 2L power 4 plus C1L. From this equation, we can write that W by 2, L power minus L power 4 by 12. Therefore, minus W L power 4 by 24. Minus W L power 4 by 24 plus C1L. From this equation, we can get the first integration constant. C1 is equal to WL cube by 24. One L is cancelled. It will, because on the left hand side it is positive. WL cube by 24 is the value for first integration constant. Clear, students? So upon substitution of integration constant into our slope and deflection equation, then we can get the final slope and deflection equations. So slope equation is that ei dy by dx is equal to w by 2 into x cube by 3 minus lx square by 2 plus c1. In place of c1, if we substitute, c1 value is wl cube by 24. Okay, students? This is the final slope equation after eliminating the constant value c1, c2 values. Then deflection equation, what it is? Eiy equal to w by 2 into x power 4 by 12 minus lx cube by 6 plus c1x plus c2. c2 value is 0 by neglect the c2 value by placing the 0 value at c2. You can write the deflection equation as w by 2 into x power 4 by 12 minus lx cube by 6 plus what is the c1 value? C1 value is WL cube by 24. So we can write it as WL cube by 24x. WL cube by 24x. C2 value is 0. So these are the slope and deflection equations, final slope and deflection equations. These equations can be used for the beam to find the slope and deflection at every point of the beam. Okay. So what is the problem in that? The question is in the problem is find the maximum slope and deflections. So where the maximum slope and deflections occurs? So maximum slope occurs at the supports, maximum deflection occurs at the center. So you have to find the slope at the end points and deflection at the center point. Maximum slope and deflections. So first of all, you find the slopes. Maximum slope in the beam is at x is equal to 0 and at x is equal to L. So at both supports, the slope is maximum. So upon substitution of x is equal to 0 into slope equation, we can get the maximum slope. So ei theta a means slope at a maximum, theta a maximum is equal to upon substitution of x is equal to 0 into slope equation. If you substitute x is equal to 0, this parameter and this parameter is 0. So right hand side, the WL cube by 24 is the remaining value. Right, left hand side we can write ei into dy by dx at a point which is maximum. Dy by dx is also write as theta. So ei theta a maximum is equal to wl cube by 24 if x is equal to 0. So theta a max is equal to wl cube by ei comes into the denominator of the right hand side parameter. So WL cube by 24 EI. This is the formula to calculate the slope at point A, that is maximum slope in the beam. So similarly, by symmetry of the diagram, we can say that theta B max is equal to minus theta A max. The magnitude wise both are same, but direction wise it is opposite. The slope at point B is maximum and that too it is negative slope minus theta A maximum. That is, we can say that theta B max is equal to simply minus WL cube by 24 EI if x is equal to L. Otherwise, you can substitute in place of x, L value, we can get the same value here. In this equation, x place lo L substitute chesna kuda, we can get the same value, theta B maximum. Okay? But by symmetry, we can say that the theta B max is equal to minus theta A max. These are the formulas for the maximum slope in the beam, and maximum deflection in the beam is at x is equal to L by 2. L by 2 means at the center of the beam, the deflection is maximum. So EI y maximum, this is the deflection equation. If you substitute in place of x, L by 2, then we can get the maximum y value. So EI y max is equal to in place of w by 2 into in place of x, L by 2. So L by 2 whole power 4 by 12 minus L into L power L by 2 whole cube by 6 plus WL cube by 24 in place of x, L by 2. So W by 2 L power 4 by, it is 2 power 4 is 16, 16 into 12 minus L cube into L power 4, 2 power 3 is 8, therefore 8 into 6 is 48 in the denominator. Plus WL power 4 by 24 into 2 is 48. So upon this, from this we can common 96. WL power 4 is in both parameter, WL power 4 by 96. If 96 is common in the denominator, we can write that 1 by 4. From this 12 into 16, by 96, then we can get the 4 value 1 by 4 minus L power 4 by 48. We can common తీస్తున్నాను. సో ఇక్కడ ఆల్రెడీ 2 ఉంది, 48 కామన్ తీస్తున్నాను. ఇక్కడ L power 4 by 48 కామన్ తీస్తే ఇక్కడ రిమైనింగ్ వాల్యూ is 1. ఇక్కడ రిమైనింగ్ వాల్యూ L power 1 by 4 మీకు రిమైనింగ్ వాల్యూ plus WL power 4 by 48. So from this 1 by 4 minus 1 is minus 3 by 4 minus 3 WL power 4 by 96 into 4 plus WL power 4 by 48. So from this 384 is the LCM minus 3 WL power 4 plus 48, 8 is 384, so 8 WL power 4 by 384. So 8 minus 3 is 5. 5 WL power 4 by 384. Otherwise maximum Y max is equal to 5 WL power 4 by 384. EI is the maximum deflection in the beam, which is occurs at the center. So upon substitution of L by 2 in place of X in the deflection equation, we will get maximum deflection in the center. Okay students, this is the maximum deflection formula for simply supported beam with UDL. Clear students? So this is the double integration method up to this problem. So in the next problem, we go for the Michaelis method. So what are the conditions? What are the conditions which are followed in the during the integration of the curvature equation in Michaelis method? So let us read that a single equation is formed. First of all, you have to form a single equation at every point of the beam for the bending moment. A single equation is formed for all loadings on the beam. M equation అనేది single equation form చేస్తాం. And the equation is constructed in such a way that the constants of integration can be applied to all sections of that beam. So that means if we take the section at a particular point, this section is applicable throughout the beam. But in previous problem, one of the problem is we solved. This is in this problem, the section is considered between A and C. Okay, this section is applicable only in between A and C. It is not applicable between C and B. So this double integration method, the section XX is considered wherever we consider the section XX, that section is applicable in between those 2 points only. It cannot be applied that section between other 2 points. Okay, if the section is beyond the load W, it cannot be applied in the double integration method. Okay, that problem, that drawback will be overcome by the Michaelis method. In Michaelis method, during integration, this XX section is applicable throughout the beam. If it is crosses the load, then it also applied. Okay, that is the point I written here. During the integration of differential equation of the whole bracket term, wherever the bracket term in the integration is assumed as a single term, then meaning entente. So I written here WL by 2 into L minus 6, isn't it? Finally, we simplified this equation. Equation మనం simplify చేసుకొని రాశాం, isn't it? L into L, L square, L into minus x minus Lx. But in Michaelis method, we need not expand this formula. We need not multiply the other term with the bracket term. So in this Michaelis method, while integration, this bracket term, whatever is in the bracket, this whole bracket term is termed as a single term. Single term means while integration L minus x, we can write as L minus x whole square by 2 minus L minus x whole square by 2. If it is L minus x whole square is there, we can write it as minus L minus x whole cube by 3. That is, it is assumed as a single term while integration. Clear? We need not expand the bracket term in the Michaelis method. Also, if the term in bracket is negative, మనం సబ్స్టిట్యూట్ చేసినప్పుడు బౌండరీ కండిషన్స్ కానీ Otherwise, something we are substituting in the bracket term. If it is negative, if we will get the negative term, it can be neglected. That bracket term can be neglected in the Michaelis method. Then meaning ఏంటంటే, if this equation is there, here L minus x is there. If you substitute in place of x, L value, it is 0, isn't it? If you substitute L by 2, we'll get L minus L by 2 is the L by 2. Like that, in place of x, more than L is there. If less than L, we can take it as same value. We have to consider this term. If the x value is more than L, then that bracket term can be neglected. This negative bracket term is neglected. Bracket lo negative vachindante, we can neglected in the term can be neglected in the Michaelis method. That is the point I written here. You have to remember these points. A single equation must be formed in the Michaelis method, and while integration, the constant of integrations can be applied throughout the beam. That section applied throughout the beam, that means. And during integration, the differential equation, in the differential equation, the whole bracket term is assumed as a single term, and if the bracket term is negative, the term can be neglected. These are the points which are remembered in the Michaelis method, which are different than the double integration method. Okay, if we solve one problem, we can easily clarify that points from the solving the problem. First problem. Let us look the first problem in the Michaelis method in this class. Remaining problems in the next class. We can discuss the remaining problem in the next class. Okay. So example 7. Here example 7 is determine the slope and deflections at the free end of the given cantilever beam when it is loaded as shown in figure. So in this problem, we have to find the slope and deflections at the free end. The free end means at B. This is the free end and this is the fixed end. So upon applying the load, the beam bends like this, isn't it? Upon application of load on the beam bends like this. The slope and deflections at point A is 0 and the slope and deflections at the free end is maximum. Deflection means the vertical displacement of the beam after application of load, and the slope means the tangent makes an angle at that point with the initial position of the beam. So this is the slope and this is the deflection, which is both are maximum at the free end. Clear, students? So the flexural rigidity of the beam is given as 10 to the power of 7 newtons mm square is given. This is flexural rigidity. EI value is flexural rigidity. So given data is length of the beam is 4 meters. A load applied on the beam, point load is applied on the beam is 50 kilonewtons, and one moment is applying. Couple is applying and the moment at the on the beam at the free end is 90 kilonewton meter, and EI flexural rigidity value is 10 to the power of 7 Newton meter square. If we convert this into kilonewton meter square, why? Because the loads given in the problem is kilonewtons. So you have to convert the newtons into kilonewtons, then only we can substitute the expressions. So 10 to the power of 4 upon conversion, newtons is converted into kilonewtons, then we can write it as 10 to the power of 7 into 10 to the power of minus 3 kilonewtons, or 10 to the power of 7 by 1000 kilonewtons. So 10 to the power of 7 by 1000 means 10 to the power of 4 kilonewton meter square. This is the EI value, flexural rigidity value for the given beam. Clear, students? So consider again x-axis section at a distance of x from the fixed support, fixed end. So by considering the x-axis, write the bending moment equation at x-axis. What is the bending moment equation at x-axis? Let us take the m is the bending moment at x-axis. What is the m value from the given problem? So how to write the bending equation here? The bending equation, bending moment at x-axis is and the moment developed by all the forces on the right hand side of that section. So here one force is there and one couple is there, one moment is there. So force, if the force is acting on the right side, we can multiply the perpendicular distance from the section to the force, then we can get the moment. And if the moment is acting on the right side, directly we can say that the moment is, if it is anti-clockwise, it is taken as positive moment, and if it is clockwise, it is a negative moment at the bending at the point XX or at section XX. So m value is, how to write the m equation, bending moment at XX. Here m is equal to minus 50 into 4 minus x. How to write this 50 into 4 minus x? 50 is the load acting on the beam, 50 is the load, point load is acting on the beam. 50 into this distance from the section. What is the distance from the section to the load? The value of the distance is distance of the XX section from the fixed end is x. The remaining value is 4 minus x. So total length is 4 meters. So 50 into 4 minus x, which is developed clockwise movement. That's why I'm taking it is minus 50 into 4 minus x. And another couple is there here. It is an anti-clockwise direction, positive couple, positive movement. Directly we can adding this 90 kilonewton meter to the given equation. So plus 90 simply. So we need not multiply the distance for the moment. Here the moment is acting at a distance of 4 minus x. Moment is acting at the 4 minus x distance. Still we need not multiply this 4 minus x for the moment. So directly we can take the moment at the XX section. Okay, if it is anti-clockwise, it is positive. If it is clockwise, negative. Here the moment is anti-clockwise direction. So 90 kilonewton meter moment is developed at the XX section. Okay, clear students? Here I am not multiplying with the distance. So minus 50 into 4 minus 6. 50 is the point load. That's why I'm multiplying the perpendicular distance. 90 is not point load. It is already moment. We need not multiply it with the distance. Okay, clear students? So from the curvature equation, what is the curvature equation? EI d square y by dx square is equal to minus m. This is the fixed equation for all the beams. Whatever the beam, whatever the load is given in the problem, we have to take this equation as curvature equation. EI d square y by dx square is equal to minus m. So from that, EI d square y by dx is equal to, upon substitution of m, minus is there, minus m. We can write it as minus 50 into 4 minus x, and the 50 into 4 minus x raskoali plus 90 on the కాబట్టి minus 90 అవుతుంది. So minus into minus into plus is minus 90. So this is the equation of curvature. So by integrating this equation once, we can get the slope equation. Left hand side EI dy by dx is equal to, on the right hand side, how to integrate according to the Michaelis method here. Cleanly observe this. So while integration of 4 minus x, we need not write 50 into 4 minus 50 into x. Like that, in the double integration method, directly we can write it as x by expanding this expression. After expanding, we can integrate. But in Michaelis method, we need not expand this bracket term. Directly, it is assumed as a single term, and we, by integration of this 4 minus x, we can get 4 minus x whole square by 2. Okay. 4 minus x whole square by 2, minus x is there, therefore minus comes into the picture. Minus 50 into 4 minus x whole square by 2. Clear students? If we differentiate this minus 50 by 2 into 4 minus x whole square, if we differentiate this equation, this expression with respect to x, then we will get again 50 into 4 minus x. Okay, let us look. So upon differentiation of this expression, దీన్ని మళ్ళీ differentiate చేస్తే మనకి ఈ term రావాలి. దీన్ని integrate చేసినప్పుడు ఈ term వచ్చినప్పుడు దీన్ని differentiate చేస్తే మళ్ళీ previous term 50 into 4 minus x term రావాలి. If we differentiate that, minus 50 by 2 is there. So differentiation of 4 minus x is 4 minus x 2 into 4 minus x, isn't it? X power n formula, differentiation of x power n is n into x power n minus 1. So n minus 1 is 1. So minus x differentiation is plus. So minus x differentiation is minus 1. So minus 1. So minus plus. So 2 cancel. So finally we will get 50 into 4 minus x. 50 into 4 minus x. Okay. So upon integration of this term, we will get the minus 50. 50 is remains, and integration of 4 minus x integration minus 4 minus x whole square by 2. Okay. Here minus 90 is there. 90 is the constant. Constant integration simply minus 90x plus integration constant is C1. Clear students? ఇక్కడ ఎలా ఇంటిగ్రేట్ చేయాలో అర్థమైందా Michaelis method లో? According to the Michaelis method, 4 minus x integration, we need not expand this 4 minus x. Directly this term is assumed as a single term, while integration 4 minus x integration 4 minus x by 2, 4 minus x whole square by 2, minus x is there, therefore put the minus sign in front of that. So minus 4 minus x whole square by 2 is the integration of 4 minus x according to the Michaelis method. So after integration first time, then integrate second time. By integrating once again, we will get the deflection equation. So how to integrate again? If we integrate this, 50 is a constant, 4 minus x whole square integration, 4 minus x whole square integration. In double integration method, you have to expand this a minus b whole square formula undi. Idi expand chesi integrate cheyali, but in Michaelis method we need not expand this expression. Directly this bracket term is assumed as a single term. Upon integration, 4 minus x whole cube by 3. So x square unte em chestam, x cube by 3 rastuntam. So like that 4 minus x whole cube by 3. So minus x undi kabatti you have to put the minus in front of that expression. Okay, 50 is also there here into 50, and also 2 is also there in the denominator as it is 2. So minus 50 is already minus is there, minus into minus plus. Okay, 50 into 4 minus x whole cube by 6, 50 into 4 minus x whole cube by 6, minus 90x is there, 90x square by 2, that is minus 45x square, plus c1x plus c2 is the second integration constant c2. C1 integration is c1 into x. Clear students? How to integrate according to the Michaelis method? I hope you understand while integrating that integration method in Michaelis method. If the bracket term is there, you need not expand bracket term. Directly you can integrate that bracket term assumed as a single term. So upon integration of minus x, we can get the minus sign in front of that expression. How to put the minus sign in front of that expression while integration. Clear students? So you have to remember these 2 points. The whole bracket term is assumed as a single term. While integrating the minus x, 4 minus x, the minus term, the minus sign you have to put in front of that expression after integration. These are the 2 expressions for slope and deflections. So we have to find the integration constants by using boundary conditions. The same boundary conditions as mentioned earlier for the simply supported beam. Here the cantilever beam is there. In this problem, cantilever is beam there. For the cantilever beam, the slope and deflections at the fixed support, fixed end is 0, isn't it? So at fixed end, we can take it as x is equal to 0. At x is equal to 0, slope dy by dx is equal to 0. At the fixed end, the slope is 0. And second boundary condition, we can take it as at x is equal to 0. At the fixed support, deflection is also 0. The beam cannot deflect at the fixed support upon application of load on it. So at the fixed end, the deflection is also 0. These are the 2 boundary conditions. So from the first boundary condition, from the boundary condition 1, what is the first boundary condition? You have to put the x place 0 and dy by dx is 0. So upon substitution of first boundary condition into the slope equation, the left hand side is 0, dy by dx is 0, therefore left hand side term is 0, that is equal to minus 50 into, upon substitution of in place of x 0, 4 minus 0 whole square by 2. If you substitute in place of x 0, this term is 0 plus c1. Clear students? So from this minus 50 by 2 minus 25 into 4 square 16, minus 25 into 16 is 400, minus 400 on this side. If you take it in the left hand side, c1 is equal to 400. Okay, c1 value is 400. Upon substitution of first boundary condition, we will get the first integration constants. Next, upon substitution of second boundary condition, from the boundary condition 2, we can say that in the deflection equation. Why? Because we know the second boundary condition, deflection is 0. From the second boundary condition, deflection is 0. So deflection y is 0, then left hand side is 0. So 0 is equal to, upon substitution of 0 in place of x, 50 by 6 into 4 minus 0 whole cube minus this term is 0 upon substitution of x is equal to 0. So this term is 0, only C2 is remains. So C2 plus 50 by 6 into 4 minus 0 whole cube. So 0 equal to 50 into 4 minus 0 whole cube by 6 plus C2. So C2 equal to minus 50 into 4 minus 0 whole cube by 6. So this value, upon calculation of this value, we can get the C2 value as minus 533.33. Clear, students? By these two boundary conditions, we can get the constant of integration C1 400, C2 is minus 533.33. So upon substitution of these boundary, these C1, C2 values in our slope and deflection equation, then we will get the final slope and deflection equations. Final slope and deflection equations. So in place of C1, we can substitute 400 value, and in place of C2, we can substitute minus 33.33. So final slope and deflections are EI dy by dx is equal to, I'm writing this equation again, but by replacing C1 value as 400. So dy by dx is equal to minus 50 into 4 minus x whole square by 2 minus 90x plus 400 in place of C1. Similarly, deflection equation EIy equal to 50 by 6 into 4 minus x whole cube minus 45x square plus 400x, C1 value 400 minus C2 value is 533.33 minus 533.33. Okay, these are the slope and deflection equations. This equation can be used to find the slope and deflections at any point of the beam, cantilever beam. Here in the problem, the slope, the question is in the problem is determine the slope and deflection at the free end. If free end దగ్గర slope and deflections find చేయాలి. Free end అంటే x value ఎంత తీసుకోవాలి? If x value is 4 meters, if x value is 4 meters, then we can get the values at the free end. So upon substitution of x place L in place of x place 4 meters, then we can get the slope and deflections. If you substitute x value as 4 in slope equation, we can get the slope at the free end. If you substitute 4 value in place of x, 4 meters in place of x, we will get the deflection equation in the final deflection equation. So slope at the free end of the beam at x is equal to 4 meters. So in this equation, by substitution of x place 4 meters. So EI theta b on the left hand side, dy by dx is written as theta. Theta b means the b is the end point if you substitute 4 meters at x place. So minus on the right hand side, 50 into 4 minus 4 whole square by 2 plus 90 into 4 plus 400. This term is 0, 4 minus 4 is 0. Therefore minus 90 into 4 plus 400, we will get the 40 on the right hand side. So EI theta b equal to 40, theta b equal to 40 by EI is equal to 40 by 10 to the power of 4. EI value is 10 to the power of 4 kilonewton meter square. So 40 by 10 to the power of 4 will get 4 into 10 to the power of minus 3, which will get in the radians. The slope is in radians. Slope value will get in radians. If you convert the radians into degrees, simply it is multiplied by 180 by pi. If you convert the radians into degrees, the value multiplied by 180 by pi. Then we will get the slope in degrees. Theta b equal to 0.229 degrees. It is in clockwise slope. Why? Because we will get we are getting the positive slope, positive value. The positive slope is clockwise slope. Okay, if you draw the tangent at the free end, it makes an angle with the initial position in the clockwise direction. That's why it is positive slope, 0.229 degrees. Clear, students? అర్థమైందా ఎలా కన్వర్ట్ చేయాలనేది? 4 into 10 to the power of minus 3 is there. 4 into 10 to the power of minus 3, it is radians, which comes in radians. So if you convert this radians into degrees, you have to multiply it by 180 degrees divided by pi. Okay, for every pi radians, the degrees is 180 degrees. Pi radians means 180 degrees. 4 into 10 to the power minus 3 radian means 180 by pi multiply cheste, we will get in degrees. Degrees loki convert cheyochu. Clear, students? Then deflection at free end. Deflection at the free end of the beam. Again, you have to substitute x value 4 meters in deflection equation. What is the deflection equation we have? EIY equal to 50 by 6 4 minus x whole cube minus 45x square plus 400x minus 533.33 is their deflection equation. In this equation, you have to substitute 4 meters in place of x. In place of x, 4 meters. Then we will get the deflection at free end, EIYB. So EIYB is equal to 50 by 6, 4 minus 4 whole cube minus 45 into x square is there, 4 square, plus 400 is x is there, 400 into 4 minus 533.3 is the constant. So upon calculation, this 4 minus 4 is 0. This term is 0 totally. So if upon calculation of these terms, we will get 346.67. So YB equal to 346.67 by EI. EI value is 10 to the power of 4. That is equal to 0.03467 meter. It will comes in meters. The deflection comes in meters. Okay. Slope comes in radians. So 0.03467 meter. Deflection is the displacement, must be represented in meters. That will comes from the calculation. It is in meters. If you convert into millimeters, this value is multiplied by 1000. If you multiply it by 1000, this value will get the 34.67 millimeters. That also downward deflection. Cantilever beam at the free end, it will be downward, displaced downward direction. The downward deflection is positive. Okay. This is deflection at free end, YB, which is downward deflection. Like this, you have to solve the problem by the Michaelis method. If you understand this problem, we can solve any type of problem by Michaelis method. Okay, so you have to remember 3 points, 3 or 4 points in the Michaelis method. First point is the bending moment equation is single equation throughout the beam. That is the first point. Second point is constants of integrations can be applied throughout the beam. Constants of integration ante manam teeskunna section XX section anedi throughout the beam ekkadaina apply chesukochu. This is the second point. And third point is during integration of the differential equation, the whole bracket term is assumed as single term. This is the third point. And fourth point, you have to remember that if you substitute the boundary conditions, while substitution of boundary conditions or while substitution of x value in the bracket term, if we get the negative term in the bracket, then that bracket term can be neglected. Clear, students? These are the four points you have to remember while integration the differential equation by the Michaelis method. Clear, students? Let us close this class up to now. Let us discuss. We will discuss the next problems in the remaining problems in the next class. Okay, students, bye. Have a nice time.